In today's lecture, we will study superharmonic resonance in the forced Duffing equation. So we will begin with the Duffing equation. That's the Duffing equation. It is forced. It is forced at some arbitrary frequency omega. There is some damping, there is a linear term, and there is a nonlinear term. Very good. Cubic nonlinearity. We will first try harmonic balance, which is familiar to you. And over here we will try 4 terms, 2 harmonics. So 1 sine omega t, 1 cos omega t, 1 sine 3 omega t, and 1 cos 3 omega t. That is my assumed solution. So let's come here and restart. When I substitute this, I get a big long expression, but I can suppress that for easier traversal. And then you see I just pick out the coefficients of sine omega t, cosine omega t, sine 3 omega t, and cosine 3 omega t. You are familiar with these. Now I have been doing this in MATLAB over here. So this is my file. You are familiar with this idea now. Omega is my continuation parameter. But what I have done here is I have used a very small value of damping and a very small value of nonlinearity, but not a small value of forcing. That is because in order to excite a strong response at a frequency that is 3 times the forcing frequency, the nonlinearity has to be active. And for that, if you have a very small forcing, that's not going to work. Very small forcing at 1/3 of the resonant frequency, the system will be predominantly linear and you won't get the superharmonic response. Okay. So from prior experience or understanding or intuition, I know that this is a parameter regime that is promising. Now I come here and I have defined my variables. These are my input variables. These happen to be my harmonic balance equation. So if you look at the first few terms, they are taken from here. They are taken from the Maple calculation. And now I have to run this, and I have already done that to save time. So I have been doing this for a while now, trying to get it into the right regime. So I've done alpha equals 0, alpha equals 0.004. I've taken small steps, and then I've taken actually a very large number of see 4200 and another 4200. I've had to take a large number, but finally I have reached a place that is reasonable. And let me plot this. Oh wait, I have to tell you what A1 and A3 is. So A1 is the square root of the sum of the first two. That means it is the amplitude of the first harmonic. A3 is the square root of the sum of the next two, so it is the amplitude of the third harmonic. Okay, so now I'm plotting both A1 and A3. Here it is. When you look at the graph, you will see this blue one. This is the fundamental. This is the first harmonic. This is the second harmonic. Okay, so the second harmonic is small compared to the first harmonic, except in a narrow region over here. In this region, I hope you will now agree that this is not far from 1/3, and we will do the analysis around 1/3. Okay, but this is on a linear scale. This blue here is the amplitude of the sine omega t term. This brown or red is the amplitude of the sine 3 omega t term. You will see that for very light damping and small nonlinearity also in our case, it sort of wakes up and the sine 3 omega t suddenly becomes comparable to the sine omega t term in some narrow neighborhood of omega equals 1/3. So this is a superharmonic resonance. You excite at some frequency and you get a strong response at 3 times that frequency. Okay, that's what we want to see. Before we continue to Maple, I want to show you the same on semi-log plots, where the amplitude is plotted on logarithmic axis, because this plot has something to show you. So first of all, you will see that far from resonance, the 3 omega t term, for example, falls off very rapidly. Okay, so this is the sine omega t term, and it is falling off on a log scale. That is because the inertial term mx double dot dominates. That's m omega square, and so the response is like 1 by omega square or something like that. But this is really small, right? So this is much smaller than that, far away. Here In the superharmonic resonance part, once again you see this peak and you see it's not far from 1/3. But this is the part that I would like you to pay attention to. On the log-log scale, you see these two curves, they nearly coincide. So for a lightly damped oscillator, the backbone curve really pretty much describes the response. And you realize there are two solutions there, one stable, one unstable, one almost in phase, one almost out of phase. And this peak is determined by, the amount of damping. Okay, so that's a good insight. But more than that, you will see that if you think of this blue as one curve and this red as one curve, the spacing between them is constant. So if you look back at my earlier harmonic balance for the undamped unforced equation, you will remember that I put the amplitude of the sine omega t term as A and the amplitude of the sine 3 omega t term as R times A, and I looked for a constant R. That constant multiplier on the amplitude, on the log scale, it becomes a constant spacing. If you think about that, you will understand what I mean. That is why these two curves are nearly parallel. Okay, they are separated by a constant distance on logarithmic axis. That means one is a multiple of the other. That just represents the shape of the waveform. Okay, and of course over here it is not like that, because that harmonic distortion is missing. At lower and lower amplitudes, the harmonic distortion disappears and effectively it is a pure sine. Very good. So that's the MATLAB intro, and now I will move over to Maple again, restart, and I now want to study this system close to a forcing frequency of 1/3. So I will play the same game. I'll think of the forcing frequency as slightly different from 1/3, and by stretching time I will make the forcing frequency exactly 1/3, but I will change the stiffness of the linear term in the oscillator. So forcing frequency slightly more than 1/3 corresponds to delta positive, because over here with delta positive the stiffness of the linear part of the oscillator is slowly going down. Okay, so this is my system. I will study this. I emphasize this is order 1, this is order 1, this is order 1. The damping is small, the detuning is small, and the nonlinearity is small. Okay, so now over here, what is my basic solution? My epsilon equals 0 solution. That's what I need to find out. Okay, so when I look at my epsilon equals 0 solution, I can even do that with Maple. What I can do is I can substitute epsilon equals 0 in dE, and then I can say dsolve for x of t. And when you do this, you see there is a sine t with an indeterminate amplitude, a cos t with an indeterminate amplitude, and a fixed part. This part is at 1/3 of t. This does not cause any secular terms. Okay, this is the part that will cause secular terms if unless they are of a certain type or nature, or their evolution has certain characteristics. So that is the criterion we will use to find out what the solution is for the averaged equations, what the equations are, what the slow flow is. So what I will do here is I will say substitute the previous into x of t, then substitute C2 control C equals a in the previous, and substitute this one equals b in the previous, and I will call this xs. Okay, so this is the solution. This is my solution. For the slightly perturbed harmonic oscillator, this term was not there. Now notice that my change of variables has a part that is linear in A, a part that is linear in B, and something added on which has a fixed amplitude and phase. Okay, so this is notice that this is a peculiar structure. Okay, now x ds is equal to the derivative of xs with respect t, so that's fine. And then what I do is I say equation 1 is the derivative of xs with respect to a times a dot plus the derivative of xs with respect to b times b dot plus the derivative of xs with respect to t is equal to x ds. Okay, let me emphasize again. People get confused, so I'm saying it again and again. This is my substituted solution, and it seems like I am not differentiating and then differentiating, so it seems like cheating, but it is not. It is a second order differential equation. In first order form there are two independent variables, x and v. X dot is equal to v. Over here what I am saying is this is v, this is x. A and b are new variables. Because my differential equation is x dot equals v, I take the derivative of this treating a and b as variable and set it equal to that. That's one of the equations. I've gone through it again. If you're still confused, please look at it again. Okay, so that's one equation. Okay, now you see this term appears on both sides, and that is not an accident. It will cancel. Okay, now E2 is equal to, and now I have to go back here into my differential equation, you see. So let me do it this way. X dds is equal to the derivative of x ds with respect to a times a dot plus the derivative of x ds with respect to b times b dot plus the derivative of x ds with respect to t. So now I've got x double dot as well. Okay, now what I will do is I will say in my substitution I have to be a bit careful. If I substitute here, then it will take derivatives and evaluate that. I don't want that, so I have to substitute in a sequence. Okay, so I say d ea is equal to E2 is equal to substitute derivative of x of t with respect to t is equal to x dds in dE. Okay, so that has been substituted. X dot is still there. E2 is equal to substitute diff x of t with respect to t is equal to what now? X ds in E2. Alright, so I've got that substituted. I still have x in it, and there is still an f in it, so that's alright. Let us hope that it works out. There should have been an f. No, this is in epsilon. That's okay. It will work out. This is inside epsilon. This part will cancel here. Okay. Then I say E2 is equal to substitute x of t equals xs in E2. And that should take care of that. Okay. Now I will say slow is equal to solve E1 and E2 for A dot and B dot. And now these are a bit long, but we'll figure that out. Should be alright. Okay. So let us see. These are a bit long, but let me see. A dot solution is equal to substitute. I should have given it a name here. Slow. Substitute slow in A dot. No, that's not what I mean. Yes, I think that is what I mean. Okay, so that's the expression. But let me do the following. Let me say combine trig. It's still fairly long, but you see all of this has zero average. This has not zero average. 0 average, not 0 average. What is the time period? There is a t by 3, so 6 pi is a safe time period, right? So I will say a dot slope is equal to integrate a dot s t equals 0 to 6 times pi by 6 times pi. Okay, I will say simplify here just to. Okay, so here is the slow flow, and I think you will agree that this is really not that different from other things that we have done. It's sort of very peculiarly similar, but we will let us proceed and you will see. Okay, so now we will do and what do we have here? What I want here is B, and what I want here is B, and I will suppress this, and then I will use that same expression here, call this B and call this B. Okay, so these are my two slow flow equations. They're a little different from what I had for harmonic balance. F cube is entering, which F square is entering here. F square is entering here, so it's a little bit different, but in some ways it's similar. And to see that it is similar, for example, we can look at the equilibria first. So this is A dot and this is B dot. I will not do the phase portrait for A and B. I could, but I will not do that immediately. What I will do is look at the harmonic balance solution. So for harmonic balance, since it is 0, I don't have to keep this 256 and epsilon and all that. I don't have to, but I can just set epsilon equal to 1 and then do it, or remove the epsilon here. So that's what I'll do. I'll come here now, and remember I have an A and a C and a delta and so on. So I have, okay, so let's move here. Let's move to this file here, and I have to have a delta. No, delta is here. This is delta. Okay, these are defined. I am not I have to figure out what epsilon is. So let us say epsilon is 0.01 or some such, it doesn't matter. So then this C is 2 and this A is 3. Okay, good. A and B are there. Epsilon was some tiny number which we are not looking at now, and then I will come here and select this one. I am only interested in the equilibria here, let me emphasize. So I will just say epsilon equals 1 for the moment, it doesn't matter. So I come here and I say clear all. I say global, and I have to define my variables. I say alpha equals -6 so that I am far from any place. A and B should be close to 0. Okay, I say y equals Newton 0s to 1, and I have some small numbers. Okay, so then I say big X. I've saved that here, and I say alpha doesn't matter. This is what I want. This should be all right. Yes, there it is. It is still going. we have to run it longer. This time I will run it for 800. Still going. Still going. There it is, it's turning back. And you can see it has moved a little bit. You see, so this starting point is about, the starting point is about 25. Now actually, if you think about when I did the harmonic balance, I had 0.02 that I made 2, right? So effectively I used epsilon equals 0.01. Okay, so from 0.33, if you look at the shift, so this is going to be consistent once you take the calculation of, account for the shift in frequency in the forcing to wherever you are here. Remember that it was close to 0.33, but more like 0.35, 0.37, and that is because of such a shift. Okay, so that takes care of the harmonic balance part. Now let us look at the phase portrait. So let us take delta as, let us take delta here at 50. Okay, so we will have C equals 2, A equals 3, and delta, unfortunately we will have to take it at 50 just to understand this. 40 or something, 50, 40. Okay, good. And then we will have to take A equals Q1, B equals Q2. Now I will set epsilon equal to 1, it doesn't matter. And then I will come here and choose this. This is A dot. This is B dot. Okay, so there is still one thing for you to see, which is why I am doing this now. This epsilon has to be removed. I think everything is all right. This number is a bit big, but as epsilon goes to very small values, that's correct. So for qualitative purposes, it's all right now. CLF, let us say TQ equals ODE45 F Duff 0 30 0.2 something. I think I have not defined OP, so it will complain. I forgot to put a semicolon. It's okay. Plot Q1, Q2. Let's see the figure. Okay, so there we have something going there. We will have to try to understand that a little bit better, but this is the not a small amplitude solution. So here A is small and B is negative, something is there. We are looking at this now, but I will say axis minus 3 3 minus 3 3. I'll get a big axis here. I will say hold on, then I will say for, some other calculations that I was doing. Okay, here f duff maybe 30. This should work. Okay, very good. So now what I will do is I'll make this figure bigger, and then I'll try different. Let's try axis this times 3, axis equal 4. Okay, so from outside large amplitude solutions just spiral in, there is no question. You see, so once again there is going to be an unstable solution here somewhere, and let's try and get a clearer view on it. Okay, what about here? Here, 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 here. There is something else. There is another game that I can play, which I will show you now, which is CLF figure. Oh, that's 2. I don't want 2. I still want 1. Axis, big axis now. Then what I will do is what I will do now is I'll maybe make it longer. I will plot it like this. Then I will say Z is equal to norm. So let me make this a bit bigger, like 130, so that it settles in. Z is equal to norm y and like that if Z is less than, I have now forgotten unfortunately what the number was. Oh, come on, here it went off. If Z is less than, I have to put a number here, and now I'm not sure what to put. So 0.7. Plot this one with B, else plot it with red, end. Okay, so small solution blue, large solution, small final state blue, large final state red. Now let us see. I forgot to put, hold on, otherwise everything is fine. Okay, I forgot to put hold on, and this will help you. Axis, axis 4. Okay, so this will help. See, large amplitude solution, so this is something I was saying earlier, I hope you remember, that from a large amplitude there are solutions that will go both to the small amplitude solution as well as the large amplitude solution, depending on initial conditions. Okay, so you can see where are the two solutions in terms of amplitude. You can see that by grid. Once you do grid, then you come here, you see this is 0 and this is 0. This is the small amplitude solution, which is we can zoom in a bit over here. So you see this is the small amplitude solution. Its amplitude is about 0.5. This is the large solution. So my guessed cutoff of 0.7 was reasonable. And you can see that from far away there are solutions that go to the small amplitude solution, and there are other solutions that go to the large amplitude solution. That's the end of this lecture. Thank you.